Okay, so the speaker this afternoon will be Tamar, and we will talk about Segal and Nikolov theorem and applications, as you can see on the whiteboard.
Thank you. So I realized today is the day that we did some break from Brauer groups, so I'm going to talk about finite groups. And I will represent the theorem of Segal and Nikolov to the search conjecture that every finitely generated finite group is strongly complete. But obviously I can't tell you all the proof because it took them 100 pages and it relies on the classification of finite simple groups. So we just make the first step that take this question and forward it to a question about finite groups. And then I will present some of the cool applications and one of mine. So what we are talking about. Let G be an abstract group. The profinite completion of G, we denote it by G hat, and later we will justify this notation, is some profinite group with homomorphism I from G to G hat that satisfies the following universal property that anytime we have just a homomorphism from G to H, where H is a profinite group, then we can lift it uniquely to a continuous homomorphism from G hat to H, which makes the diagram commutative. And actually, it's enough to consider only finite groups here. So it's very easy to see that if the profinite completion of G exists, then it is unique. And it also always exists for every group G. And it's defined by the inverse limit of all the finite quotients of G. So say G modulo A, where A is a finite index normal subgroup of G. This makes an inverse system. So we take the inverse limit and we get the profinite groups. It satisfies this condition. And it also satisfies the following properties that the homomorphism I from G to G hash is injective if and only if G is residually finite. Which means that the intersection of all subgroups of finite index is trivial. And also the image of this homomorphism in G hat is dense. So the image of G topologically generates G hat. If G is not just abstract group, it can be a profinite group itself. It still has a profinite completion. So if G is profinite, it also has a profinite completion if we consider G as an abstract group. And it's very surprising, but G hat may not be equal to G. Why this happened? Because not every homomorphism from G to a profinite group or finite group, it doesn't matter, it's continuous. And actually, we know that if G is profinite, then it is isomorphic to the inverse limit of all the quotients of the form G modulo O, where O is an open normal subgroup of G, while we say that G hat is the inverse limit of all the quotients of this form. Now, every open subgroup is always of finite index, but the converse is not always true. And we will give an example. So the most simple example of subgroups of a profile group which doesn't equal to its profile completion is if we take the product of Aleph0 copies of CP, where P is some prime, then this is also, okay, first, this is the profile group, and it is also a vector space over Fp. The dimension of this over Fp is 2 power 2, it's 2 power Aleph0. So how many maps it has to CP? In order to define such a homomorphism, it's enough to define just function from a basis to CP. So there are 2 power Aleph0 possible functions. So it has at least 2 power Aleph0 subgroups of finite index, but it has also Aleph0 open subgroups because it has the Aleph0 basis of open sets. Yeah.
View this as an abstract, but it comes with the topology, the product topology.
Yes, with the it's the product topology.
With the product.
Okay.
There's a reversion of the axiom of choice in here. Can you give an example with that?
No, I don't think that exists. Oh, yes, we need the axiom of choice to say it has a basis. Really. And we can generalize this example to the power, infinite power over some infinite set of every, say that this occupied for a finite group, which a finite group. And then we can take an ultra product, we can just divide by some subgroup that generates one ultra filter. But again, ultra filters require the axiom of choice. So I think it's very, we need this. So if G does, if G equals to G, we say that G is only complete. G is strongly complete if G equals to G hat, and we saw an example of a group which is not strongly complete. Actually, most of the group are not strongly complete. After you see one example, you understand that there is no reason that the group will be strongly complete because we can define maps to finite groups which are not continuous. And this is equivalent that every finite index subgroup is open. And obviously it's enough to consider normal subgroups because every finite index group contains finite index normal subgroup, and if a subgroup contains an open subgroup, then it is open itself. So the famous conjecture of CERN is that every finitely generated for a finite group is strongly complete. It was open many years, and there were partial solutions just for finitely generated abelian for finite groups, and then finitely generated for P groups. And eventually in 2007, Segal and Nikolov, Dan Segal and Nikolai Nikolov, prove that the answer is yes. And as I said, it is really, it's not simple at all, the proof, but we will see the first step, and then we'll see why this is so important to the whole theory of finite groups, not just finitely generated. Okay, so we need the following definition. Let W be a group word. Then we say that W is D locally finite if every group that generated by D elements, if H generated by D elements and H satisfies WH equals E, where WH is the subgroup generated by all the words when we use elements of H, of course. Then H is finite. So this is a definition for abstract groups. So the first step of the proof was to say the following. We need to prove that every finite index normal subgroup of the finitely generated finite group is open. Actually, it's enough to prove that for every, let G be a degenerated for a finite group, it is enough to prove that WG is open for every W, which is a D-locally finite word. For every D-locally finite word W. And why is that? So let's O be a normal subgroup of finite index in G. We want to show that O is open, and that's why we call it O. So G modulo O is isomorphic to some finite group H. And H is still degenerated. So let's look at the free abstract group FD that generates over X1 to XD, D elements. And we look at all the homomorphisms from FD to H. And then we take D to be the intersection of the kernels of all such homomorphisms. Free from FD to H. So H is finite, and there are just finite many such homomorphisms. So D has finite index in FD. And thus D is also finitely generated group. So D is generated by some elements of the free group, which are just words in the generator. So this is W1 in X1 XD and then WN. But notice that if we take these words and we substitute another element from the free groups, then the element we accept is still in D, because it will be in the kernel of all the homomorphisms, because we just can define another homomorphisms which sends the generators to the same elements. So we get that D is actually generated by one element, which is the word, which is the product of all these words. Till W N Y N. And we call this word W. Then W is a D-locally finite word, because every group which is degenerated and satisfies W is the image of FD modulo D, which is finite. So W is D locally finite word, and since obviously H satisfies this word W, then WG is contained, this is a subgroup of O, because G modulo O satisfies W. So if WG is open, then also O.
So when you say that H is generated by one word, is that as a normal subgroup?
And no. Okay, okay, we don't need that D will be generated by this word, but
Or is it T?
I want to say that no, it is. Why not?
Otherwise, it is cyclic. So
No.
Need to add more variables, no? You can add more variables than different variables.
T is a T subgroup. What's this?
Just a minute. What do we need in?
Take the free group of DLG items.
No, I don't want to put elements in this at all. I just want to say this is just a word, and we can substitute any elements in this elements. And what I want to say is that if a group satisfies this word, then it will be the quotient of FD modulo D.
Oh.
Okay.
Yes, that's what we need. Yes, this is not an element at all in the group. Just consider it as a word. Okay. So we need to show that WG is open, and the next step is that WG is open if and only if it is closed. Again, we talk about the locally word W. Okay, every open subgroup is closed. That's always true. For the second direction, if WG is closed, we know that every closed subgroup is the intersection of all open subgroups that contains it, and if it's normal, it's the intersection of all normal subgroups. So WG equals to the intersection of all O. O is normal, open in G, and contains WG. So we want to show that there are only finitely many such groups. Okay, so G modulo O satisfies the word W, and W is the locally finite word, so G modulo O must be finite, but this is not enough. We know that this is a quotient of FD modulo D. So it is all these groups are quotient of some finite group. G modulo O are all quotients of FD modulo D. So there are only finitely many subgroups, and how many homomorphisms, continuous homomorphism, because O is open, are there from G to a finite group. G is finitely generated itself, so there are only finitely many such homomorphisms, and that's what we needed to show. There are only finitely many open subgroups which contains WG, so WG is the intersection of finite open groups. It's open itself. Okay, so what we need to show is that WG is closed. Now, WG is equal to the union of all, we denote it by WG power n, which is just a multiply of n elements of words in G. And this is just by definition, the group generated by the words. So WG is closed if and only if it has finite length, which means that there is some n such that WG is equal to WG power n. Okay, so again, this direction is clear because it makes WG the quotient of powers of G, which is compact, so the image is compact and that's closed. And for the second direction, WG is union of closed subgroups, closed sets. There are not subgroups. Union of this, as we said, they are all closed. So by Bier's category theorem, I'm not sure. I'll write here. One of these sets must have a non-empty interior. So there is some coset of an open subgroup in WG, which contains in G W power M. Okay, so all these elements can be written by M products, and this is an open subgroup, so it has only finitely many quotients, and then makes WG as the product of some n plus k elements. If we take k to be, say, the maximum of all the other representatives of the H, when we take all the representatives of O in WG. And eventually, it is easy to see that I don't know. So WG is G power W power n if and only if it holds for all the finite quotients, continuous finite quotients of G. WH equals GW power n for all finite continuous quotient of G. So we will get that every finitely generated profinite group is strongly complete if and only if the following property holds for finite groups. Every finitely generated profinite group is strongly complete if and only if for every D locally finite world. There is some number f of w and d, which depends only on the world and d, of course, such that for every finite group, G, which is generated by D elements, WH equals to H W power this number. I mean that this number doesn't depend on the group H itself. And this is a question about final groups. Obviously, this is the hard part, but we will stop here.
You don't need that theorem. You just that theorem is not needed. It's for the implication of the utility.
What?
When you apply that theorem, it's for an implication that won't be used in practice.
Yes, because I only needed the other direction, but we want to say that it's equivalent.
Sure.
Yes. And why this theorem is so important? It gives information about finitely generated profile groups, but it actually gives a lot of information about all profinite groups, which most of them are not finitely generated. When I say most of them, I mean most of the interesting profinite groups, like most of the absolute Galois groups, are not finitely generated. But this helps us understand them too. And actually, some of the applications I am going to show you proven before the conjecture solved, and people just say, if Searle's conjecture is true, then there will happen many good things. So first, we notice that let G be some profinite group, not finitely generated, not necessarily finitely generated, and A is a finite quotient of G. Then A is isomorphic to some quotient of a subgroup of a continuous finite quotient of G. A is isomorphic to a quotient of a subgroup of a finite continuous quotient of G. Because we can take just a finite number of elements such that all the we just choose pre-images for the elements of A, x1 to xn, and we take the closed subgroup they generate in G. So this is a finitely generated profinite group. Every closed subgroup of a profinite group is profinite too. And it projects on A, and this projection is continuous because every subgroup of finite index in this group is open. And now it's known that, okay, so there is the kernel, say, equals to U, and the topology on a subgroup is inherited by the topology of the group. So U contains the intersection of this group with some open normal subgroup of G. So G modulo U is the projection of Okay. A is isomorphic to H modulo U, which is the projection of H modulo H intersection with O, which is a subgroup of G modulo O. And why this is good for us? Because it says something about the possible finite quotients which are not continuous of G. If corollary, if G is a Rossi group, where C is some variety, where C is a variety of finite groups, which is closed under subgroups and quotients, such as P groups or nilpotent groups. Then every finite abstract quotient of G also belongs to C. Every finite abstract quotient of G belongs to C, which is actually equivalent to say that G is also a pro-C group. G is a pro-C group. And another corollary is that the order of G equals to the order of G, because again, the abstract quotient doesn't add any power of prime, which doesn't divide the continuous finite quotient of G. And this helps us to give an example of a strongly complete group, which is not finitely generated. Yes.
What do you mean by the order? Do you mean as a supernatural method or?
Yes, supernatural method.
The theorem? Do we need really the theorem to get this corollary?
No, there are other proofs, but this is the simpler. Yes, it's not okay. We don't need it, but it is still a application of this theorem. So, if the order of G will be a product of primes with finite powers, then G is strongly complete too. Then G is strongly complete. Because actually G is always a continuous quotient of G X. We just can take the identity homomorphism from G to G. So it's a homomorphism from G to a profinite group. And we can lift it to a continuous homomorphism from G X to G. And okay, it will be epimorphism. So the order of Gx equals to the order of G times the order of the kernel, but they are both equal and all the powers are finite, so this must be equal to 1. And then G equals to Gx. For example, if we take the product of Cp over all primes, this is a strongly complete group which is not finitely generated, which is more surprising after we So the example, and actually there are very few subgroups, profile groups which are not finally generated and still strongly complete. There must be countably generated, and they must have also only finite abstract quotients of each index. Okay, so now I need to show something new. I plan to talk about projective groups, but I promised Ellie to talk about messy products. I didn't prepare it, so maximum you will need to help me. We're mostly interested in finite groups when in the context of Galois groups. And one of the interesting questions is which profinite groups are absolute Galois groups? Which profinite groups are absolute Galois groups? So there are some restrictions of the properties of such groups. And for example, one of them is that, okay, there is some condition about the homological ring of the group, but it also has a equivalence condition by embedding problems. So every absolute Galois group satisfies the following property. For every epimorphism from G to the group UN FP, okay, that's the quotient, which is the upper triangular matrices, I think, elements from FP, and this element is from it. We can sort of lift this homomorphism to an homomorphism to UN FP, but it doesn't make this diagram commutative. It makes another diagram. We get here another element, but these elements are the same. Okay, and the other elements can be different.
The next diagonal above the ones.
Yes. We have this strange condition.
Also a quotient. You can divide by all the diagonals of this one.
No.
So,
Yes, but this is not what we want, because we want to know that you can complete all these elements. Okay, so absolute Galois groups has this property, and also we know that every closed subgroup of an absolute Galois group is also an absolute Galois group. So we actually interest not in groups that have this property, but in groups that every closed subgroup has this property.
so UN bar is question of UN by just a single
Yes.
element. Okay.
Yes, by
And then the other
This
thing is
group.
question by
yes,
Okay.
we divide by this group, and
Then you
we
divide by the
don't
other
need to complete the diagram, but we need to send it to another element just to save the secondary diagonal.
When you say that absolute Galois groups have this property, do you assume anything about N?
Oh, yes, n equals 3. But the conductor is that it also every n. Yes, no, I didn't prove it for every n. But since we seek for subgroups, it is a, and as I said, most of the absolute values groups are not finitely generated, then it is interesting to point out that if G satisfies this property, then also G hat. G is the n-vanishing messy product property. I will call it the strong property because I want it. I want every closed subgroup to satisfy it. We get the same for G hats. Okay, so we have the homomorphism from G to this group, an epimorphism. I prove it for every n, but we just know that for n equals 3, every absolute value group has this property. This is finite group. So let's take a finite set of preimages, A. Now for every finite subset, say B. In G, we look at the closed subgroup generated by A cap B. So it projects over UNFP, denoted by HP. And again, this is the closed subgroup, so it's as the vanishing messy product property, and it's finitely generated. So this homomorphism, okay, I'm sorry, I just need to start with the epimorphism from G hat, which is continuous, but it equals to epimorphism from G, which is not continuous. That's what I forgot to say, because the image of G in G hat is dense. So if this is a continuous map, the image of G will be dense in the image, but the image is finite, so it's discrete. So we look at finite, not necessarily continuous such images. And if we can complete this diagram in an abstract homomorphism, then we can lift it to a homomorphism from G hat. So we start with a continuous epimorphism from G hat, which induce abstract epimorphism from G, but these epimorphisms are all continuous because this is a finitely generated or finite group. And also there are, so we can lift the diagram to UNFP, which the property we wanted, which is not exactly a commutative diagram. Also, we just have finitely many such options. Again, because this is a finite group and it's finitely generated, then we look at continuous homomorphisms. Now, if B embedded in C, we have a function from HC to HB because we can look at the restrictions. So we have a inverse limit of finite sets. And we know that the inverse limit of finite sets is never empty. So it defines a abstract epimorphism from G to UNFP, which the property we need, and we can lift it to epimorphism from G hat. I think it's a good point to stop.
Other questions?
Do you have an example where you have a Galois group and its profanity completion is also a Galois group? Or
You mean absolute value?
absolute Galois group? Yeah, I'm sorry. Is there?
See too.
Okay.
Now, how much examples do you have to absolute values?
No, I'm thinking, so how to use this result, thinking about how to use it, so you want, you're saying that if the profanity completion is not a Galois group, then the original group is not Galois
Yes.
group either. Just
But
trying to think of
to
examples.
prove that the point completion is not a Galois group, it's not simpler.
Do you know anything about,
Please go ahead.
do you know anything about fields for which the absolute Galois group is not found?
Most of the, just if it's not finitely generated,
So this is the expected.
yes. Because if it's not finitely generated, there are just a few combined groups which are still strongly complete. So I guess they are not absolute Galois groups like the example is.
Do you believe that if G is an absolute Galois group, then so is G hat?
Yes, this is just one example of property that we can lift from G to G hat, but there are more.
So do you believe that if G is an absolute Galois group of some field,
I think
G hat
so.
will be any group?
Just because the three properties I know, that's all.
Try to attribute your conjectures to other people.
I only know three properties of the Galois groups, and they are all preserved. Yes.
Maybe continuing in that vein, what do we expect the field to be?
That's a good question.
There's a problem set. Yes.
It's a good question, and maybe that will be the next step.
Other questions? Then let's thank the speaker again.